So see, when we talk about prompting or the topic of prompting, so far we have gotten used to an approach in which we feel it all boils down to giving instructions to a machine in natural language, isn't it? We speak in English, we structure it using different templates. For example, the co-star template. It does surprisingly well, but the problem with templates, the problem with English language is that it is there is a problem of non-determinism. Sometimes it works, sometimes it doesn't work, right? And that is one aspect of it. It has to do with the fact that, and we were talking about it a little while ago, but I'll rephrase. See, if you look at the target space that a machine hits, if you look at a machine, let me take a more control perspective. Where's my white color? Here. Suppose you have a machine. This is your LM, language model. Huh? I'll use the word language model, LM. That's it. So suppose your input goes in X. This is your input. Every machine, from a mathematical perspective, is nothing but an output, y hat, is this, right? And then a language model is autoregressive. In other words, this goes y hat I goes back in to produce the y hat. So y hat I, so you just say that input is xi and input xi plus 1 is xi and yi up to y0 all the way to yi that has been produced, right? All the previous tokens that you have produced, they go back in, and that the language model is going to produce some output, the next token based on that. That's what a language model is. Inherently, because you do a sampling of the softmax, because you sample off the tail end, sampling is inherently a stochastic process, right? You lose determinism right off the bat. You don't have a predictable answer. It leads to a host of problems, or with the language, with the English language itself. English language itself is, or any language, spoken language, natural language, has inherent ambiguities, isn't it? In fact, that's how lawyers thrive, because there's ambiguity in the natural language. Two people disagree. They may sign a contract. Both of them have different interpretations for what it is, or different expectations, right? So language is ambiguous, and a language model is trying to interpret the language and make something of it, and make something of it in a non-deterministic way. Do you see how complex it is? And a language, the natural language, is inherently very sensitive to small perturbations. So you change the, one example, there's a famous book, Eats, Shoots, and Leaves. Based on where you put the comma, let's say in one, you put the comma here, eats, shoots, and leaves. That seems rather murderous. You go to a restaurant, you eat, then you shoot, and then you leave. Alternatively, if I put the comma here, eats, it shoots, and leaves, we are probably talking about a panda, right? And here, we are probably talking about a killer. So you see the sensitivity to semantics from just a token misplaced here or there, right? This is for English, actually. In other languages, it gets even more extreme. Here it was a comma. It's true for every language. For example, in a language that I speak, Urdu, and I won't tell you, there is some of you. How many of you understand Hindi and Urdu here? You do, right? So there is a little saying that says, "Nukhte ke her फेर में खुदा जुदा हो जाता है." What it means is, Nukhta is a dot. Where you put the dot will turn the word God into the word God. Gone forever. So that, right? So those are the nuances with language. Natural language has subtleties. And for a machine to really understand those subtleties exactly is hard, no matter how much data you feed into it. It does an admirable job in that. To complicate the situation, human beings are imperfect typists. We make lots of typos, spelling errors. We altogether forget the punctuation. So if I remove the punctuation from this, just says, eat shoots and leaves, you realize that the meaning of this sentence becomes completely ambiguous. You don't know which of the two interpretations to go for, right? So that speaks to the nature of natural language. Then you have, to make matters worse, a stochasticity in the response itself, right? That's why people call it the stochastic parrot. Now, if you are trying to build something of value, how would you do that? Here is the traditional way people do. Suppose they write a LLM, what these are usually called LLM applications. What do? You write a system prompt. You write a system prompt which anticipates the nature of the user prompt, isn't it? You very carefully do that. Throughout the course, we have been creating the system prompt. And what you would do is you would write an app in which the user prompt, whatever the user gets prefixed with the system prompt. It goes into an LLM, out comes a response. And you expect the response to be exactly fulfilling the needs. Right? It's an application. But as people are finding out through hard experience, it is rather tough to write the perfect system prompt. Has anybody experienced that? Right? All of us, isn't it? You think you got it right till another user input comes, and that makes your system prompt look like some monkey wrote it. Right? It's pretty frustrating. And what happens is, typically and this is the real life experience, in software houses, engineers are told they need to create a system prompt. And this is an example of user inputs they'll have. And the product team would often serve maybe a list of 20, 30 examples, user inputs. What will happen is they will write a system prompt that works for those 20, 30 examples. But does it work in production? It's a touch and go. You don't know. What happens is that your system prompt, this is very important, system prompt overfits to the training data. Are we together? Or to the user, to the sample, to the exemplars. To the exemplar user queries, right, that your product team might have given you. Anyone knows this from experience? It happens.
So my experience is that the LLM sometimes ignore.
Microphone. Yeah, good. Yes, it is. I can hear you now. Yeah.
Oh, so my experience is that whether you put in the system prompt or the user prompt, the LLM sometimes ignore direct instructions. How does that happen?
Because your system prompt, that is another issue. Very good question, Vasanthi asked that. Sometimes the LLM altogether ignores your instruction, which is one of the dangers. right? Because there is another system prompt baked into the machine, censorship baked into the machine, that somehow deems your system prompt to be overridden, and it overrides it.
But, okay, I'll give you an example, right? I said, give me, in my system prompt, I said, just give me the prompt, do not over explain, do not explain it, do not, just give me the prompt, right? It seems like a very, innocent instruction, right? So what?
No,
if
you forgot to give the format of the response. If you straitjacket it into the format, it must be like this, then you're not just saying don't over explain or anything. You just say it strictly, it must be this.
Yes,
Give the
so maybe I'll show you later on, but it
Yeah.
feels like I have capitalized it. I kept saying, do not explain, right? Like bold letters, and it still ignores it. And that was, I just found that very strange.
Yeah, capitalization on the web usually means shouting. So maybe the LLM said, "What a rude fellow! I'm going to ignore this." No, I'm kidding. So those are exactly the pathologies. And would you not like to know that there is a way to fix all that? Who would like to know that? So I hope this has gotten you interested today. That's exactly what we are going to talk about. So the way that we are going to look at prompts today, and as I said, I'll give you the core concepts because today I want you to learn by doing it. It is this. 1 second, I'll just turn off the lights. So it is this. You give what the input should be with the question, for example. Let's say that you're doing question answer. You expect that the user will give you a question that you have to answer. Are we together? So you could just say, go answer this question, the user question, but you might want to put some safeguard, some context and so forth. You do that. Then what you do is you give it a few examples, few short learning, right? That for question Q1, answer should be A1, Q2, answer should be A2. These are good examples that you give. This is an example of few short learning, isn't it? Or something like that. Interestingly, what if you did not have to have the headache of writing the English at all? You just give it a starter format, or a framework just has the starter formats built in. It's basically saying a common use case is question answer. If you get a question, just answer it and just say with a factoid or something simple. Answer it. And if there's a context, use the context. Then what can happen is, let us say the machine, so here is an LLM. What can you do? In the beginning, LLM is pre-trained. You can't touch its weights. We'll come to a different way. Now, think about it this way. Why is it that you get different kinds of responses from the LLM? If you really think about it, what happens is that user input, even though you think you're saying the same thing, but using different words, no, it is triggering different circuitries within the LLM. Right? You remember the LLM is vast, and the signal transduction that takes place, it doesn't equally go through all of those neurons. Some neurons are going to be fairly passive about it. So there will be only a sub-circuit that gets activated, isn't it? Based on which sub-circuit gets activated, your response will appear. And so if you change the word slightly, your responses will change. So the question is, suppose we do this. We start with a prompt, P0, right? And you let it, so first of all, you define your problem. You define your problem using what is called a signature. In this framework, DSPy, signature. In any problem, you have to give a signature. What is the input? So you'll have an input field. If it is text, just leave it as that, input field. You may have an output field. So question, for example, is an input field. Answer is an output field. So you're basically declaring, and for simple things, you don't have to write all of this. You can give it in a simple sort of a string notation by saying question, response to question is an answer. Are we together? So you're defined what the problem is, what's the application that you're trying to build. It's question will lead to answer. Question is the input, answer is the output. Are we together? If you want to make it a little bit more sophisticated, it could be question, context, answer. Or if you were doing it here, you would add context. Is also an input field. You just declare what all goes into the element. So far, so good, guys? Then what you do is think the way a neural network learns. How does a neural network learn? See, what you do in PyTorch is, what do? We have lots of neurons. We just create a layout of the neuron and so forth. You take a neural network, something. What do? You give it data. You give it literally one training data, A1. You tell it the problem. What is the problem? You say it's a classification problem. Right? What does this machine do? It will create a loss based on y hat y. Am I talking language that's easy to understand, guys? Right? It will produce an output. So your signature is declaring what is it that we want to do, right? In either a simple string format or using a class. You're just declaring the nature of the task classification. Then you need to give it some data. That data will lead to some output, some answers, isn't it, guys? That output may or may not be what we expect. Does that make sense? It may not be what we expect. And one of the things that happens is, even if you don't give an output, what happens is that this machine, these frameworks that we are talking about, DSPy being the leading, it could write a little prompt, see what the output is. It may internally decide, I don't like it. Maybe I need to improve upon it. And it might write a different prompt and a different prompt till it feels it's getting the right answer. Right? So it may have internal validation checks in there. But better still, what can you do? Very much like a neural network, what do? You backpropagate the gradient. Yeah. Backprop. And who does that? The optimizer does that. Remember from the theory of neural networks, we have optimizers like Adam optimizer, stochastic gradient optimizer, this and that optimizers. What do the optimizers really do? They change the weights and biases of the neural network, isn't it? But in the case of our LLM, most of the time, you don't have access to the weights and biases. I mean, you can't change them, right? Sometimes you can, but most of the time you can't. You don't fine-tune the weights and biases. But you do have one lever to control, two levers to control. What is it? Your system prompt? Yeah. And user prompt should be later on, whatever the user will enter. But you do have a control over the system prompt. And what you could do is, for example, if you give it a question and it produces an answer, predicted answer, and you have the real answer, labeled answer, you can do, this becomes your loss. The gap between the answer that you expect and the answer that the machine gave, that effectively becomes you can derive a loss function from it, isn't it? Do you see that, guys? By saying how different is the answer from what I would have expected. So let's make it very concrete. Let us say that your problem is sentiment analysis. So you want to make sure that the sentiment analysis comes out as positive, neutral, negative. One of these three. You ask the LLM, you give it a few statements to always predict in this set. Right? Now, there are two pathologies that may happen. One is the LLM may say a word bad or angry. Sentiment is this. None of these words belong to the list that you provided, right? So it is basically giving an answer that for you is non-usable. Are we together? Or it may just answer with a statement saying the sentiment expressed is, and this is a problem, Vasanthi, that you are feeling. Sentiment expressed is positive. You didn't ask it to say the whole sentence. You just wanted to get the word positive. And nevertheless, you can't stop it. It's rather garrulous, right? And it will give you the whole sentence. These things happen all the time. Either it doesn't produce what you expect, or the evaluation itself may be wrong. You say it's positive sentiment, and it says that no, it's negative, or whatever it is, right? It may have wrong answers. So you may have pathologies of multiple kind. It may give an answer that's simply not in your list of possible answers. It may give it in a format that is incorrect, or it may pick one of the answers, but it isn't the right one in your training data. All of these are pathologies. So now comes the question. Your data set, training data set is there, right? What is it that you can change? Now, think about it in the way I say. I say that it is a function of the, let's just write it as two functions. You have an input, user input, X, that gets augmented to a complete with a system prompt. It gets augmented to GX, right? That goes into an LLM, and LLM produces a Y hat, roughly speaking, which is, it is the LLM function applied to G of X. You see that, right? Now, you cannot tamper with the LLM function itself, except that the LLM function is stochastic. It keeps changing, but that's all right. What can you change here? What is in your control? G. This is in your control because this is engineered by the system prompt. Isn't it, guys? This is what you can control. So you know that if you do any kind of perturbation to G, it is going to directly impact the output. So therefore, if you treat the words in the system prompt as effectively parameters of a machine learning model, because as far as the application is concerned, the entire thing is a machine learning model, isn't it? Including the weights of the LLM, as well as the wordings in the system prompt. They are all parameters of the model. And that's why people say that in these frameworks, you think of weights and prompts, by prompt meaning the system prompt, as the parameters of a bigger model that you are fine-tuning, that you are basically doing a learning on. Because what does in a neural network, what do? You do a backprop on the loss to change the values of the parameters, isn't it? W prime is equal to W minus alpha, gradient of the loss. That's what you do, right? Or more generally, in the presence of an optimizer, it is minus a learning rate scheduler, let me just call learning rate scheduler, times the some gradient function, some function of the gradient of L, like if you're using an Adam or one of the more sophisticated optimizers, but basically it's the same idea, much more sort of sophisticated. So the question is, if you could treat the wordings in the prompt as something you can change and see whether you get a better response, not a better response for just one answer, one question answer pair, but for the whole training set, right? Wouldn't it be better? And so there was a discovery that led to all this. People found that you could actually sometimes what looks like the sensible prompt, sensible system prompt that you would write in common sense English doesn't perform as well as some very idiosyncratic prompts, right? Very weird prompts that you do by making mutations in the words, right? By changing the language and throwing in all sorts of additional words and things like that into it. Am I making sense?
So another way to solve this problem is using instructor, right? Because you
Instructor doesn't make your machine learn. Instructor just says output must be in this format. That's all.
right,
Instructor is never about the input prompt. It's only about the output.
but the end result could be the same. You want your output in a certain
Yeah,
format.
you control the output. That's all. But what happens is that it may give you the output in the format you want, but it may be the wrong output. The answer may be wrong.
The syntax will be correct, but the semantic might be
Meaning
not
would
what
be
you
the-
want.
Right? So because of that, you realize the problem is, and this was the innovative idea, what people realize is that what machines consider good prompts and what you consider good explanations are two different things. And at the heart of it, it has to go. And anyway, I won't go into too much of this mathematics here, but within the LLM, there are sub-circuits that get triggered. And in a way, and now we know, for example, that there are features. For example, we know one of the Anthropic's great discoveries was that in the belly of the LLM, if you dissect the brain, you literally find concepts. There is a concept for the Golden Gate, there's a concept for psychoprancy, and so on and so forth. Right? So suppose you wanted to always answer positively, right, or politely or something like that. A little bit more than normally an LLM would do. You just need to make sure that certain specific circuitries are triggered. How do you preferentially trigger certain circuitries in an LLM when you don't typically have access to the weights? I mean, you're not going to change the weights. Right? If you could, then of course you can go and emphasize that circuitry. But since you cannot, what can you do? What people found is by changing the system prompt, the wordings in the system prompt, and making it weird, like to a linguist, to a literature major, they would look like weird changes you're doing to the language. But it makes sense because each of this system prompt is nothing but, it's in a mathematical sense, it's just a g of x. And the only question worth asking is, well, what is that optimal function g that can be applied to the user input such that it leads to the results that we want? Are we making sense? Isn't it? So what happens is this g is weird. In a neural network, these things are weights and biases. But what they are saying is this G is actually in the space of words. And words can be changed. And the text can be changed. And for every perturbation of the text, if you change the text to something else, you know that the response will change. But then you say, well, you know what? If you're going to change my text, there are infinitely many texts that can be written. How would you know which is the right text? Right? And that is exactly the problem that optimizers in machine learning solve, isn't it? They find they have efficient means to zoom into the right parameters of the model. And in the breakthrough work that we are referring to, which led to the concept of programmatic prompts, and that is why, you know, I said that I don't like the word prompt engineering because prompt engineering word has been hijacked for writing prompts in English. Right? And today I'm telling you that don't bother writing your prompts in English. Instead, let the machine, because your prompt, your system prompt is your G, let the machine dynamically through a process of optimization discover the best prompt. Wouldn't that be lovely? Right? Because we are all good at writing code, much more than writing lots of English text. Right? So this new approach is actually the state of the art. So now you say, now, wait a minute. Did I just pay tuition for this course only to be told that don't do it anymore? Right? Well, actually, that's exactly what I'm saying. Right?
So it's no longer revenge of the English majors.
No longer the revenge of the English majors. The time is come and gone. Well, let's not get too kind of. I mean, they still have some use, but here's the thing: DSPy, and it's the beginning of something really big, right? The programmatic access. So I'll tell you something. See, I grew up in the mountains, in the Himalayan mountains, as you know, my childhood. I don't know if I told you guys, and because of the problems that happened with China and Tibet, a lot of the Tibetan refugees used to live in the mountains. So I lived literally very proximal to the Tibetan culture. And part of their culture is deeply imbued with Tibetan Buddhism, a form of Buddhism. So they have a beautiful custom. I've always loved that custom. What you do is, before any of the great events, right? So, for example, there is this event that is, they call it the Kala Chakra, in which, let's say, somebody big, the Dalai Lama would come and he would give his benediction for his blessings to people who have been waiting for the event. What they would do is they would create something called a mandala. Right? They would take beautiful colored dust, a chalk, and make an elaborate sort of a symbolic drawing on the floor. Beautiful patterns they would make. And they would, like, it would take days to do it, painstaking effort and days. And it would be an absolute picture marvel. I mean, you have to see what those mandalas that these people make, these monks make. So after they have made it, guess what would happen to the mandala? Yes, exactly. With just a hand, you just wipe it out. So the point being, I suppose, that it is not the mandala. I mean, there are multiple things. They speak of non-attachment and so forth. But more than that, they want to emphasize. Also, there are many other meanings, but importantly, they are emphasizing that it was worth knowing how to make the mandalas, that going through the process, because it was for them, I suppose, a form of meditation or a form of prayers to build it. But having built it, it is of no more value. Right, and no point in being attached to it or something like that. So I'm reminded of it in this course. Now that I've taken you through the whole journey of learning prompting so well, it isn't that it is useless. The learning is useful because many situations, you don't want to write a very programmatic. You don't want to go through the exercise of lots of, like, typically, if you want an answer to a question, you would go to a language model and quickly ask that question and get an answer in English. It might not be the perfect occasion to do an elaborate programmatic exercise. Right? But for anything serious, and especially if you're building an application, I would strongly urge you to use the programmatic approach. Change over to the programmatic approach. So now you may say, now what about my co-star and all of that? Same thing applies. You can do your co-star, which was a template, but you can actually reproduce it in a programmatic manner. And I would strongly suggest take a programmatic approach to it, right? The other advantage of a programmatic approach is that you can, just like code, a program, you can concatenate, you can compose bigger programs out of smaller pieces. It has composability. Programming always has composability. So you can create actually a multi-step complex task that you want LLMs to do by creating individual tasks. Now, when you do the individual task, in reality, what happens is if you do it by hand, you keep on perfecting each little piece of the journey, right? You break the task up into pieces. Those of you, I asked you guys to write a business plan. Did I ask you guys to do that? Glossary and the business plan, right? So, and then to do self-critique and all that. So each of these, you write little prompts and then you try to make them perfect. Problem is, in a garland, it sort of beads. Each of the bead is perfect. Nevertheless, the garland might be too heavy or too uncomfortable or whatever it is, isn't it? Some situation. In other words, micro optimization Local optimizations do not necessarily always add up to a globally optimal solution. It's a fairly obvious statement in mathematics, but just making it real. What happens is you may get each of your little task pieces, subtask pieces right, but the overall solution may still not be quite what you expect. And if you play around with prompts a lot and build LLM applications, yeah, which seems to be the dominant way these days startups are coming up in Silicon Valley. So this becomes altogether very familiar. So you can ask this question: why am I doing gradient descent on? So why am I optimizing each of? Why can't we use a programmatic approach that will, in a sense, do a gradient descent? That will, in a sense, do optimization, right? Learning and optimization in the space of all the G's, G1, G2, G3, all of those tasks, text prompts, and co-optimize them all. Does that look like a more sensible approach, right? Why not co-optimize them together to get a result set that is robust, that is stable, and that is optimal? Make sense? So that is the broader context of frameworks that are emerging. Two dominant frameworks that have emerged are DSPy and TextGrad. Grad, by the way, is not for graduate, it's for gradient descent, right? Yeah. Emphasizing the fact that you can do, in some sense, a gradient descent on the textual landscape. Text is the pieces of the system prompt, the text is the landscape of parameters over which you're doing gradient descent. The loss function and gradient descent is taking place, right? And what happens is you have made the problem into a problem of supervised learning, isn't it? You realize that creating prompts, especially if you give it a lot of training data, sample training data set, you have made it a problem of, isn't it supervised learning now? That's how you do supervised learning, right? What do you do in supervised learning? You have a data set, xi, yi, right? You have this data set, training data set, train. You create a model, instantiate a model. You do the forward pass, predict y hat, create a loss, yi hat, backpropagate the gradients, update let me just use the word parameter, P, update the P's, the parameters, right? The same thing, all we are saying, what these guys are saying, this is, we are going to do this time-tested approach, except that the optimization that we do, since weights cannot be changed, are frozen. Actually, even the weights can be changed, but let's take that as a separate issue. But by properly changing the system prompt systematically, you can essentially ensure that the right circuitry in the LLM is triggered so that the answer is consistently optimal or what you want it to be. Right? So, Sushant, you should be getting an idea of how I engineered my security guard. Right? So, see, all my secrets are there, are in the open now. Create good classifiers, create good prompts and things like that. And you have a winner. The problem is most people don't spend time and effort to do that. So now let's look at a real one. By the way, guys, is all of this making sense to you?
Yes.
It is making sense. It's
I have a
straightforward.
question though.
Yeah.
How do you measure the difference between y hat and y when you're generating text? Like how good is one piece of text versus the other? Two sentences can mean the same thing, slightly different.
I had the same question.
Oh, you also have the same question.
The loss function, how do you determine the
That's right. So see, the loss is determined. You need some metric, like loss is usually, for example, a mean squared error or something like that. These are metrics. So you're asking, how will the LLM, how will this framework know or measure is the answer good or bad? Or how does it compare?
kind of addition to that is like when we do programmatic, thing. So maybe we might do it initially, we might create it manually and then test it out. And then, once we think, okay, that this program seems to be working, okay, now let's do 100, 1,000 or whatever.
Yeah,
Right, at that point, when we try to scale it, we still have to make sure those loss functions are working right.
that is right. That is right. So the whole question is who gave us everything is clear. You have the system prompt. You can start with some framework that will auto-generate a starter system prompt and then go optimize from there. What is the core value, or how is it that you measure loss? What answer do you expect me to give? Well, you'll be surprised with the answer. Anybody would like to take a stab at it?
So, you just ask the LLM which answer is better,
No.
and then.
Don't. Don't, because it will say, of course, I'm right. I answered it. How many times have you seen the LLM confidently tell you that it answered it correctly? Yeah. In fact, people are observing that. Somebody told me that they like the new Owen model that has come out from OpenAI. But the only thing is, when it is wrong, it is very insistent that it is right. And very confident. It says, no, I've reasoned it carefully. It is right. Right. So, so you don't ask the LLM. So how do you do that? Anybody else would like to take a stab at this? Any guesses? How do you quantify the loss? How does the framework quantify the loss? So here's what it is. You don't ask the LLM. About whatever else you do, don't ask the LLM. There are two ways. The framework says for some situations, some simple ones, it can compare. It will just do comparison between, so you can do a causal loss between the output text and something. So for example, if it was supposed to be positive and the word negative comes out, it's obvious it's wrong, isn't it? So it can be told. And you can look at the logics and so forth. But more specifically, what it says is that in the best practices, you give it the function that compares the LLM output to that. And within that function, you can put in whatever you want. Right? So for example, in the sentiment analysis case, it's very obvious. You compare it with the answer. Right? If the answer if it doesn't match the answer, you say bad. You say 0. If the answer is good, I mean, things like that. You realize that, right? You can give it a goodness metric, and if the answer matches, you call it 1. Things like that. So it is completely up to you. It's called the metric. You can specify your own metric, but most of the time, if you don't specify the metric gets implicit, right? By comparing it with the actual text of the answer, the system will do a reasonably good job of it. So both of these frameworks, DSPy and TechSquared. And now what has happened is this work came out of Stanford in our neighborhood. And yeah, go ahead, Shishan.
Good question. So here, the loss function of yi comma y hat I. So y hat is what the LLM generates, right? And the y is what we expect.
Yeah, answer.
So in terms of scaling, we don't have the yi. Right?
No, yi is what the LLM generated. Y hat.
Yeah.
Y hat. And yi is the answer that you have in your training data set.
Yeah, but when we try to scale, we don't have like 1,000 yi.
Yeah. So whatever number you have, you try it out.
Okay.
So that is a very good question. See, what happens is that, and now let me come to the real practical things to it. See, guys, if you are doing this in enterprises and companies, you'll see, you go to a developer team. Developer will say that, okay, I can write a system prompt. Tell me, give me some examples to test it. The test data set would be small, isn't it? They will give you about 20, 30, 40. You can train. No, I'll come to that. Hold your questions 1 second. I'll come to your question. So what happens is that given the fact that you have just 50, let's say, or 100 test cases, would you rather trust an engineer or an English major to go and tweak the text, or would you trust a mathematics to do a more optimal job of creating a better prompt in a situation, right? Which is more likely to succeed. And what you will find is that engineers get bored, or human beings get bored. They will tweak the system prompt, and after a little while, they will stop iterating over it. Because human beings can, like, how many edits have you ever made of your own paragraph? Like, how many of you can honestly say that you went beyond 50 edits? You don't. That's where machines shine, because a machine can, if you look at the permutations it's making to a prompt to achieve a result, it will go through hundreds or thousands of mutations. Think about it this way, thousands, way beyond what you and I would do, thousands. So what is the downside of it? Well, if you're using one of the cloud LLMs, they rejoice because your token count just went up, isn't it? To create the perfect application. It's a one-time cost. I'm just joking. But obviously, you make lots and lots of calls. The machine goes into a very tight loop. It keeps doing all sorts of optimizations. And before you know it, many of you will start hitting your token limits and whatnot, right? It's a flood of requests going there. But at the end of it, assuming that your token limit is generous and the model is powerful enough, you do that. The second thing that happens, as I know all of you have questions, I'll come to it. The other thing that happens is, guys, reality is you validate your things with frontier models out there for which you pay. Once you know that the problem can be solved, guess what you do? You repeat it with a smaller in-house model. Because if it succeeds also with a smaller in-house model, you have the cake and eat it too. Because when you take it to production, you are not paying a recurring per token cost to the cloud providers. Do you see that, right? You're not paying a recurring cost to OpenAI or to Gemini or to somebody. So almost always from economics perspective, you keep repeating it. And then new model comes and new model comes. So what happens is that same input, XI, same output, YI, a data set, you will realize that you need different prompts for different LLMs. Right? And these prompts are extraordinarily hard to discover manually. Right? But once your code is written, and those are very few lines of code, Python code, and after that, you just ask the machine to go discover it, the best prompt for each of the LLM. So that is the power of using frameworks like this. Are we getting that? That is the power. Because the same code base will auto-generate. And you can ask it to, one of the things you will do is you will ask it to produce you the history of prompts. And you can literally see how it is writing better and better prompts and doing it. And I'll finish that because I can see questions on almost every face here. Does this work? Or is it all just theory? Does this work? Actually, it's not a perfect tool. It's work in progress. But as far as I have seen, it beats humans hands down. Right? It beats us hands down. Now, the other aspect that comes in is you can sometimes, it is not that hard to create training data. Right? Sometimes you can create a massive amount of training data. But the bigger the training set you have, the harder it is to do it manually. Because when was the last time you saw an engineer run their system prompt on all the inputs, verify that all the outputs are essentially right? Because now you can't just compare word by word. You have to read the output and compare it to the reference output and see how different they are and sort of grade it, put a score next to it. And then go change the system prompt. Let's say you have 1,000 instances, go through the exercise and then do 1,000 iterations. In other words, 1,000,000 observations. How many engineers are willing to do that? They are not. Right? So from a pure scalability perspective, right? But you realize that if you could create a training data set, that if this is the input, this is the output that I expect, if you could cheaply create such data set, it would terribly go against human prompt engineering, but it would exactly fall in favor of programmatic approaches like this, because a machine, a prompt that works for 1,000 cases is likely quite robust, right? So the exercise that I gave you to generate, classifier and so on and so forth, can you guess how many, what was the size of my training data? Make a guess.
So training data as in the data which you generated finally?
Yeah, to train the classifiers. And one of the classifiers was using an LLM, another one was using an encoder, right? So I trained a whole collection, ensemble of classifiers to do that, which you do, like when you go real production and when matters are really sensitive, you go overboard. So what you got is a simplified version of it. But can you guess what's the training data set size I created? Anyone?
Yeah. 10,000.
10 million.
Oh, wow.
10 million. Right? So can you imagine a machine that achieves area under ROC curve of 99%? Would you trust that machine with your security at that moment to safeguard your data? Isn't it? You're pretty confident about it, isn't it? That's what you try for. It's hard. It's a lot of hard work, actually. These problems are harder than you think, but it can be solved. The point is that, and it's not easy. You have to use an ensemble of approaches so that the ensemble's overall accuracy of the area under ROC curve is that high. But you can do it. But see, if you were training an LLM, then you realize that it's hopeless. Human beings are not going to sit and optimize their prompts. You have to do it programmatic. The limitations of this at this moment is that at this moment they solve it, but if your problem, there's up to a complexity limit till which they work. If the task is more complex than that, then gradually the bets are. So they're trying to push the frontier. These are all new frontiers. See, all of these things have just appeared within the last year or so, right? And it's a very fast-moving ship. But the reason I'm mentioning it to you, actually, it turns out that most people don't even know that these things exist. And if you're doing anything serious except just basic prompting, I would always say do programmatic prompts. It just works simpler. And once we are all familiar with Python code, isn't it? For us, it's no-brainer. And actually, we can produce this code in less time than we would keep on scratching our head. I mean, many developers come and tell me that any given day, I would write 1,000 lines of Python code, then 2 paragraphs of English, because you feel so frightened writing English text, isn't it? Right. So this is in your familiar territory. It is totally in your familiar territory. So that is the value of frameworks like this. And so with that, now I'll take questions. Vasanthi, I've been waiting for one.
Yeah, so when you talk about loss functions and optimizing, my mind directly goes to training an LLM. But it sounds like
No, you leave the LLM alone. Remember, see, this is what I'm saying. Go back to this, the way I presented it. Input, user input goes in. There is a G function that acts on it. What are the parameters of the function, the system prompt, the tokens in the system prompt. And then there is the LLM that acts on top of the G, right? So what you get is this. The output is the LLM of the G of X, isn't it? In effect, well, that's oversimplifying it because I didn't put the causal nature, the fact that generated tokens are fed back in, but let's look at it like that. Okay. So input is this, and let me just say, output is also the tokens that have been generated by I minus 1, right? LLM of GX and Y0, Y. I minus 1, up to this point. All of that, the LLM consumes and produces the next output, right? Now, what is in your control, for sure? Definitely in your control. The function G. How can you change the function G? Of course, if it is a function, you can change it. You can optimize it. And the only question is, then you realize that, oh my God, G is not made up of actual floating point numbers. It's made up of words. And that was a roadblock till somebody has had an epiphany that, hey, words, numbers, for what? Let's change the words itself. It's a discrete change, but let's go changing the words themselves and see what happens.
Okay, so G of X is where you apply the loss function in the optimization.
Yeah, yeah. I use the word loss function. Most people just use the word metric. Yeah. What is your evaluation metric? So you have a function that will just say given y hat, given y, return a score, how good it is.
Okay,
Maybe you
how-
can say 0 for bad, 1 for good. No, just return a number. And then what the machine will try to do is be as good at it as possible. It will
that
try.
would be money creating that metric.
Yeah, so it's a very easy thing. You just create a Python function and you give it to the machine.
You get the output of that Python function to the machine.
No, you give the function itself to the machine and say, use this. Use this to judge the output.
Oh,
See, suppose I write this. Let's write it. Suppose it's sentiment analysis. Y hat and Y, you're comparing. What would your implementation be? If Y hat is equal to, because these are both strings, is equal to Y, right? Let's say return one if this is true, else 0. You see, in one line, you wrote the evaluation function. And you give this function over to the machine. You say, hey, okay, go create a good sentiment classifier, the sentiment analysis program for me.
So in this case, if it said good versus positive, this would come out as 0, so it would go and try to fix it.
Exactly.
But if it's negative versus positive, it's still going.
It's still go, yeah. So this is a really not a good one because good is a little bit closer to the right answer than negative. No. So I just wrote the most primitive one. You can write a smarter evaluation metric, evaluation function. All you have to do, so what do you need to give in? You just need to see in reality, and let's get to the practical aspects of it. See, what you do is you need to declare what task you're doing. That is in DSPy, there's a signature class. Signature, right? Which tells the inputs, outputs. As far as the machine is concerned, that is what it is, right? Inputs go in, outputs come out. Inputs are usually the user prompt. Remember, you don't mention system prompt. You just say user prompt and sometimes a context. Right? Some basic context that may be a system prompt. I mean, a context that will remain the same. Like, for example, if you say we are specifically talking about generative AI. So it is some context, right, which cannot be further optimized, or more or less. It is about, that's it. It's a hardwired info. And then you give the output. And then you can give some training data train. You can give it an eval metric. And then you can specify which optimizer you want to use. Just like guys, do you notice that, does this look like Python, PyTorch? If you're familiar with PyTorch, which all of you are, right? PyTorch, is this not exactly that? You're basically saying, I'm going to train a network. Now go train it. And they literally use the language of PyTorch. DSPy has aligned it to. So they literally say forward pass. The forward method produces the prediction, that next token, y hat, right? The def forward in these classes, in their modules is, and they even use the word module, just like PyTorch uses. So what they have done is they have made it mimic the PyTorch API so closely that if you are familiar with PyTorch, you should find it easy to understand and learn. Now, this is one of those frameworks that despite it being there, most people are confused. And this is one of those situations where the creators of DSPy thought they have done such a good job explaining it. What more do we need to say, except to say that it totally looks like PyTorch, right? And then people who don't know PyTorch are scratching their head and saying, what just happened? I have no idea how this works. right? What is this whole optimizer business? By the way, to add to the confusion, the optimizers they used to call the teleprompter, right? For some reason. But so, and the API has slightly been changing. So with all of that preface, let's go and look at the, look, oh my goodness, I have to get your lunch. 1 second. I will just introduce you to it and I'll walk through it. Today, I want you guys to do it on your own to some extent. Sorry. Let's go here. So go to this URL, DSPy-docs version app. First, we'll start with the cheat sheet at the top, because that says a lot, right? So forget about the data loader for the time being. I would say that make yourself familiar. Let's go to the tutorial, not tutorials, DSP. Using DSPy. Oh, by the way, this paper is fairly good. The unreasonable effectiveness of eccentric automatic prompts. Let's start with a quick start. Installation is easy. Right? If you're going to do a RAG, which of course you are, right? I would suggest not just install DSPy, but install the QTrend also. Right? We will need QTrend. Do it like this. Here's the minimal working example. Work your way through this, but let's look at how this whole thing is working. Right? This machine actually, so, and this is what I felt about the documentation. It seems is very well explained, but it isn't. People tell me it is not so obvious that it is. So first is you take some, the fact that you need some training data, isn't it? Supervised learning kind of an approach. So you can go to the GSM. These are general math problems, school grade general math problems data set. So here is it. Can you see the nature of this problem? Natalie sold chips to 48 of her friends in April, and then she sold half as many chips. Chips in May. What's that?
If you are playing
NVIDIA. Good. How many chips did Natalie sell altogether? This, right? And so here is the answer. So guys, do you notice that you want your machine to reason like this? Now think through. What is the approach that would work best? You have been doing prompting. If you want your machine to produce an answer like this, what is the specific design pattern that you will use or approach of prompting you'll use? Chain of thought. Remember chain of thought, right? Now what happens is that to train a machine to answer these questions, right, you can give a few examples. Right. But see, this data set already has examples. So you can train a machine to do chain of thoughts on its own. Right. You can, let's look at this example. What are we doing in this example? The first is just getting the model, an LLM, setting up the language model. Right. I would strongly say just go with 4, don't go with 3.5. Or if you want to start with this, token limit is 250, just to keep it small. DSPy, you need to tell it which language model to use, right? By the way, in the beginning, use OpenAI, but I would rather that you used local models like Olama and your local model, whatever is the biggest model that can run on your machine. And of course, on the support vector machines, you can easily run 70 billion parameter models. Right? It's running there on the inference, so you can connect. Now this is the math data set. Load math questions from GSM 8K. Why do we want to do that? Why do we? It's just supervised learning. That's what you do. You load a data set, split it into a training set and validation set, isn't it? Don't you do that, guys? When you take a supervised learning, you break it up into training. They call it the dev set for some reason. Now let's look at what the training and dev sets are. So you can print out a few lines and we already saw what it is. We didn't have to print out, but they're just taking 10 examples. So it is a 10 shot, like if you think of it as few shot learning, it's 10 examples. So you can just look up the first 10 examples here. That's what will go into the machine, right? Then you're defining. Now look at this, guys. Does it remind you of PyTorch? Literally, instead of NN module, you're using DSPy module, isn't it? You're in effect creating a neural network of sorts, except that it's not made up of weights, it's made up of, well, words. Yeah. Internally, that will be discovered. You do that, and you choose. This DSPy comes up built in with some of the common patterns, like chain of thought is built in. You do that. Now, by the way, this is giving the signature. I don't give signature like this. Question leads to answer. It's a very succinct way of saying that it's a simple question answer thing. Input is question, output is answer, right? I like to do it a little bit more formally. I would create a signature object. Remember, I said signature object specifies the input output. No, I would create a signature class and give an instance of the signature object a little bit more formally. You do that. Now let's think through it. You create program. Now, what does the actual thing do? Look at the forward pass. In the forward pass, in a neural network, what do you get? You get the input and you need to produce the output. Is that what it is doing? It's returning the answer, which is just the forward, just applying your built-in chain of thought upon that question, right? Just doing that. Now what happens is you have no idea what is internally written, what prompt got internally written. You have no idea, isn't it? No. All you know is you created a network, and this is the biggest point. You have completely divested the responsibility of creating a good prompt in this situation. Do you see that, guys? You wrote no prompt. You just wrote code, Python code. With that now,
Sorry, yes, sir. I'm trying to, well, I know a little bit PyTorch.
Little bit.
Yeah, so I did some neural nets, but the thing is self.prompt. What is prompt?
Oh, it's just a variable name. It's just a name of the program. In other words, the thing that will produce, basically it sits upon the LLM and uses chain of thought. Like, look at that.
These are the model, it's like
it's sitting upon the, no, what you call it is that chain of thought is a built-in, it's a built-in module internally. What it does is it has reference to a LLM and it will create its own prompt, system prompt. Just think of it, it will create a system prompt. It will take your query, pass it to the LLM and give it. So in other words, if you think in terms of this,
I understand what it's doing, but I'm trying to understand the syntax of how they did it.
Yeah, that is exactly.
It's not so intuitive. But
it's not intuitive at all. That's why people get so lost with this. So this is it. Do you see this yellow box that I drew?
Yeah.
In this particular example, this is that program, the self.program that you see, prog.
Oh, it's a program.
Chain of thought. Do you see that? This program, because what is it internally made up of? It will create its own chain of thought prompt, system prompt.
Right.
Right. And it will use an LLM to produce an output. Right. So,
yeah. But what is the question goes to answer? Is that just some plain text name of the model, or is it some syntax?
No, it is just a syntax. It says that to all of these, you have to give signature. If you look at the chain of thought class, the input is a signature. You can give the signature in a more formal way, but they also give you a shortcut. The arrow says left of the arrow is the input, right of the arrow is the output.
And here's the name. The question is going to be the name of the input.
That is it. That's all it is. Right. And again, I take slight objection to it. As I said, right, I would not have put it so cryptically. I would have used my signature class. Signature would have said, question is the input field, answer is the output field.
Right. Yeah.
Right. So to the same bit of code, let me say how I would have written. I would have written it a little bit like this. Signature. Yeah. If you want my signature, right? But let's say question. field, answer, output field. And here I might have also put a little bit of a description saying up to short answer less than, let's say, suppose you're doing sentiment analysis, you would have said one word, but because this is a chain of math question, less than, let us say, 20 tokens. Like, don't go verbose. Don't give me a full explanation. Just tell me the answer. Right? This sort of thing. And now you get this. And then what would I have done is I would have said a signature. Let me just say sig is equal to a signature object. And then that object I would have given to DSPy, the chain of thought. So chain of thought is an internal method it will use. It needs to know what is the input output. And there I would have said sig. Okay. I would have written it a little bit more layout and written it more formally rather than so this. And yeah, that is one of the things many people have said, that they find the documentation rather. It is both clear and not so clear. If you know what they're talking about, it becomes clear. But it's like, so it takes a little time to break into it. Now, what else do we need? When you create a neural network, remember, you need an optimizer, right? You need an optimizer. And you need an evaluation method also, of course, some metric. Yeah. But even if you don't give so here is what you do. Observe that we can, this GSM 8K, they have built a metric already. What is a metric? When you're doing an arithmetic problem, there's only one metric. Answer is right or wrong, isn't it? I believe so. You can look up the implementation of this, but my guess is that it's a binary thing. So here is the way you need to configure something like how many demos to set up we want to bootstrap 4 short, like how many 4 short examples, right? How many examples do you want to give? In each time you invoke the LLM, how many examples do you want to give? So you say 4, max level demos 4. That makes sense. Optimize it. Now to optimize, you need to give an optimizer. So bootstrap few short means bootstrap means I'm not telling you even a starting prompt. Go discover it. From a few short examples, go discover it. You need to give it a metric, right? You give it a metric. And then what do you do? And here is where the thing, I hate this language. It says teleprompter. I would have used the word optimizer. Like if you really want to align with PyTorch, you better call it the optimizer, isn't it? I would have named the variable optimizer, optimizer.compile. And this is your COT. Where is your COT? Here is your COT class. Do you see this? You just created your own class. So COT, yeah, you give, sorry. Let me go up a little bit. COT. So now the word compile is different from, I don't know why they did not simply use the word optimize. Right? Optimize is optimize. Yeah, that would have been a more intuitive naming convention, but they call it compile. Right? And so there are little oddities with this framework, but it does work actually. So you give it, and now training set, you give it the training set to learn from. And so it will go at it. And then if you want to, now that you have a compiled, and this is the thing, compiled, optimized DSPy. Yeah. Let's move to evaluating its performance. So always you do an evaluation, right? You can evaluate. How do you evaluate? You would take the test data now and then see how well it does on the test data. You would evaluate, right? So evaluation is using a metric, isn't it? This is it. Now, the rest of it is just to show progress, this, that. Inspect. Now, one more thing, you may be curious. Okay, this is all fine, but it all sounds so black boxy, isn't it? You have no clue what prompt it wrote. So to transition from a world in which you spend so much time thinking, discovering a prompt, to a world in which they're saying, oh, hands up, we'll take care of it. You're nevertheless curious, how exactly did it do it? Right? You want to see the trace. So what you can do is, if you want to just see the most recent final prompt that it discovered, you can just say, inspect history, give you the last item, right? On the other hand, what I would suggest is, look up the whole history and see how it is optimizing. Yeah. It is really, really worth seeing its previous prompts. Right. Now, one more thing I will say, there is more to it, but I'll leave this today as an exercise for you guys to carefully study DSPy, guys, the whole day, just study DSPy, right? Because I'm here, I'll help you. I'll go, we have to go get your lunch. Now, one thing I'll say, does it actually work? It works really well, but it takes getting used to. And the fact that the documentation is something that many people have said, oh, you know, I couldn't make head and tail out of it. Right? That's a bit of a dead trend. I wish there was a really good book or something out of it. But if you're familiar with PyTorch, then it seems more or less explanatory, at least some part of it. And you also have to know what the machine is doing, that it's going to alter. It will keep mutating until it finds the good prompt. So today's your task is to learn DSPy really well, guys. Today is the day for DSPy. Does it work? I'll show you something. I'll show you a project. Storm. DSP. Stanford, they created this, and there's a paper started. I will read this paper in the afternoon. There's a research paper, etc. What does it do? You can actually go and cloud credits for discounted. I don't think it helped me at all. Choose an account. Well, you can get it and run Storm. When you do run Storm, you can ask it to write a full Wikipedia style article on any topic you want. Right? Now, writing a Wikipedia article has multiple phases. You know, it has to search the web, it has to do this, it has to gather information, it will do all of that. Then it has to format it in a Wikipedia style, which has an initial description, a bit of history, a bit of explanation, details. You see that? Now, when you were doing your business plan or your glossary, you realize that getting it to work really well is hard. And you can imagine that creating a full Wikipedia style article is actually a bit hard. So one of the tasks that you can do towards the end of the day is set this up locally on your machine, the Storm. Just run it, give it your Wikipedia, some topic, and see the output. It is completely done or predominantly done using DSPy and is a resounding validation of it. Very practical, very useful. You can use Storm actually to do write-ups on many topics. Right? Now, some of you, anybody here who's in my agents class? Right. So you would say that if prompting goes so far, what about multi-agent systems? So somebody has created a multi-agent version of Storm called the Core Storm, I believe. Right? Even more powerful. And at the end of it, you go from what is the revenge of the English majors to the demise of the English majors. Because this begins to spew out articles, fairly high quality, fairly good articles with very little effort on any topic you want, detailed articles and so on and so forth. So I want you guys to get started with this. And with that, I'll end today's session. In fact, I'll end the theory. I may do a paper reading in the afternoon, but by and large, today I wanted to be